All right, hopefully you can hear me. I'm going to go through the practice exam really quickly. Here we go. All right. So question 1, a blank is a neutral molecule or ion that acts as a Lewis base with a central metal atom. So these are the things that are going to bind to that central metal ion and form a complex. And in that case, that is a ligand. Ligands are those Lewis bases that bond to our central metal atom. So all of our K sub F and our table that gives us our K sub Fs are related to that. Our solution contains 9.74 times 10⁴ molar silver nitrate and sodium cyanate. After solution reaches equilibrium, what concentration of silver remains? All right. So this again is chapter 18. What we're going to have is, here we go. Normally, we would have, we're going to have silver nitrate, and we have that silver cyanide. We're going to have that cyanide atom present. Easier, let's write it like this. So I've got silver nitrate as a solid, and as that dissolves, it's going to give us aqueous silver ions and nitrate ions. Then the other reaction we're going to have, once we have those aqueous silver ions in solution, is those cyanide ions are going to be present, and it can complex with those. And if we go to the last page, in the for the table of all the constants, at the end of the exam, we'll see that it forms a complex with cyanide that looks like that. And the K sub F for that is 1 times 10 to the 21. So pretty large there. All right. So then what we're going to do is focus on the formation of that complex. The silver ions, we have the KSP there, and we can figure this out. And I believe our concentration is low enough, or actually we don't even need it, such that we can assume what complete dissolution of that silver nitrate, and the concentration of the silver then, because it's 1 to 1, being 9.74 times 10 to the negative 4 molar. They don't give us, okay. And then we have the cyanide and its starting concentration. There's 1 cyanide for every sodium cyanide. So it's going to be equal to its molar concentration. And then we're going to form our silver nitrate here. And that has a really large formation constant. But at the beginning, we just have the silver cyanide in solution, and then none of the complex is formed yet. All right. So because we're going to have a really large K sub F, a really high likelihood of forming that complex, we can assume that we're pretty much going to complex almost all of that silver away. So then we can determine how much cyanide do we think we're going to use. Well, there's a 2 to 1 ratio of silver to cyanide, so we should be able to react away 2 times that here. So 2 times the 9.74, or come on, 1.948 times 10 to the negative 3. We're going to lose that. We're going to be left with X amount of silver. We're going to form right around that much of the complex. So then 6.52 times 10 to the negative 2 minus 1.948 times 10 to the negative 3 gives us 6.325 times 10 to the negative 2. So we have everything we need to put into our case of F. The case of F for this again was, dang it. The case of F is 1 times 10 to the 21, that's right. And that's going to equal our products. In this case, the silver cyanide complex over our reactants. That'll be the Cn minus and we need 2 of those, so that should be squared, and then our silver, which is just going to be X. So if I carry this out, what do I get? 6.325 e to the negative squared. Okay, 9.74 e to the 4 negative divided by 4.001 e to the 3 negative divided by 1 e to the 21, and X should be equal to 2.44 times 10 to the negative 22. So pretty small concentration, which is what we would expect with such a large formation constant. And there that is, yep, answer A. Okay. 3. Identify the processes. Identify the process in which entropy decreases. So we want a negative delta S. An increase in the number of moles of gas would give us a positive entropy phase transition from a gas to a liquid. That would be less disordered to more, so that would be negative. Solid to a gas would be positive, and a liquid to a gas would be positive. So the only possible answer here would be B, phase transition from a gas to a liquid. Spontaneous reaction occurs without outside intervention. We're not so much concerned with heat. That will affect it, but not always in the same way. Sometimes heat will, exothermic will result in spontaneous or non-spontaneous. Same with endothermic. Most basic definition, spontaneous reaction occurs without ongoing outside intervention. What's the value of delta S surroundings at 298 degrees for the following chemical reaction? So we want delta S surroundings, and delta S surroundings is equal to negative enthalpy system or reaction over T. So if we're at 298, all our answers are in joules. So I'm going to convert our 66.4 kilojoules to 66,400 joules over our temperature, which is 298 Kelvin, and then we're going to put that negative sign in front of that. And that's going to give us negative 222.8 joules per Kelvin. Or, so yep, rounding up, we're looking at answer B. All right, under which of the following conditions would the reaction be spontaneous? All right, so we've got a gas plus 2B, a gas going to C, which is also a gas, and our delta H is negative 50 kilojoules. So our delta H is negative. That would mean our delta S surroundings should be positive. And our delta S of our system, if we look at this, we have 3 gas molecules going to 1, so our delta S should be negative. So what we're looking at, if we want a delta S universe that is also positive, and our system is negative, but our surroundings are positive, then I need that positive value to be larger than the negative value. This is going to happen when t is small, because we're dividing our delta H by t. So we'll get a larger positive value for delta H when t is small, and there's a greater likelihood that that positive term will be larger than that negative term, or the magnitude of it will be. So should be spontaneous at low temperatures, which is C. Okay, below what temperature does the following reaction become non-spontaneous? So we're not too concerned with what the actual reaction is, because they tell us our delta H of our reaction, which is positive 136.5 kilojoules. And they give us our delta S of our reaction, which is positive 287.5 joules per Kelvin. And we're looking at our Gibbs free energy, and we want a Gibbs free energy. They want us to know when it becomes non-spontaneous. So when does it go from negative to 0 and then to positive? So right at what point would it go from 0 to positive and give us a non-spontaneous reaction? So I'm going to convert this to joules. Keep this in joules. Oh, there, joules per Kelvin. So I'm going to set delta G equal to 0. Carry over our delta H, so subtract 136,500 joules from each side. And then if we're solving for T, divide both sides by 287.5. Technically, sorry, there's a negative term in front of that. Gets us temperature of 474.8 Kelvin. So once we go above that, below that we're spontaneous, and above that we would become non-spontaneous. Or wait, no, negative, positive. Yeah, we have, or no, we want a negative. So yeah, above that temperature we'd become spontaneous, and below we'd be non-spontaneous. So there's our answer right there. B is when it would become non-spontaneous. The other temperatures are even lower than that, but it's not becoming non-spontaneous, it is non-spontaneous at that point. So the answer there, yeah, B. Calculate delta S for the reaction, and we have our equation for NH3 gas plus 5 O2 gas goes to make 4 NO gas. and 6 water vapors. And we're told the standard entropy for each of these, 192.8, 205.2, 210.8, and 188.8. So products minus reactants, so I'm going to have 4 times 210.8 plus 6 times 188. Oops, sorry. 188.8 minus 4 times 192.8 plus 5 times 205.2. And what do we get here? One, 7, 6. It's 178.8, and that is answer B. Calculate delta G under the condition shown. So we have non-standard delta G. So we're going to use the, it should be delta G equals delta G standard plus RT ln Q. This one I left off of here. I should have. Okay, so we're given our standard delta G. Here we go, question 9. So standard delta G is negative 180.8 kilojoules. I'm going to convert that to joules because R has units of joules per mole Kelvin. Our temperature, they tell us is 298. And then ln of Q, we're looking at water being a solid, so we are going to leave that out, and then we're just looking at our 2 reactants, which are gases, which are the mercury, or not water, mercury oxide, sorry. But the mercury and the oxygen are both gases, so we're going to look at the pressure of the non-standard pressure of the mercury, and that mercury has a 2 in front of it, so we're going to square that, and then the oxygen, which is 0.047. Okay, so we're going to take give a 1 over 1.0575 times 10 to the negative 5, and that is 94,000. We take the natural log of that. Five, 7, and multiply that by 8.314 times 298. So I have negative 180,800 joules minus 28,386 joules. We get negative 209,000 joules or 209 kilojoules. So what is oh, it's 1 divided by, that's what I did. That should be positive F. Yeah. So yeah, this is a positive value here. So this should be addition negative 152 kilojoules. It becomes less spontaneous. That should be answer E. Uh, 10, what's the value of microstates in a perfect crystalline solid at 0? Should only be 1 microstate available. And then when you take a log of that, you get 0. Your entropy would be 0. So the answer there would be B, 1 microstate. Balance the following redox reaction. So we have Fe 2 plus MnO4 goes to make Fe3 plus and manganese 2 plus. Our oxidation states are plus 2, plus 7, minus 2, plus 3, plus 2. So manganese is reduced, iron is oxidized. We'll start with the iron. I think that'll be the easier one. It's oxidized to Fe3 plus. That should just be 1 electron that it's losing. For the manganese, we have MnO4 minus. It's going from a 7 to a 2. So it's gaining 5 electrons. Going to Mn2 plus. Now the manganese are balanced, but the oxygens aren't. So I'm going to add 4 waters to this side to balance the oxygens. Now they're balanced, but I've got 8 extra hydrogens on the product side. So I'm going to add 8 H pluses here. And this is an acidic solution. So we're all done there. So now I just have to look at those number of electrons. We have 1 here. Come on. 1 here and 5 here. So what do I need to do? Multiply the top by 5 to get it to balance out. So I'm going to end up having, come on, 5 Fe2 plus 5 Fe3 plus and 5 electrons, and then those can cancel. We want to know the coefficients for the hydrogen and the iron. So for hydrogen, the coefficient's going to be 8. And for the Fe3 plus, the coefficient's going to be 5. So that's going to be answer A. Calculate delta G at 298 under the conditions shown. So very similar to the other reaction. Duplicate question kind of by accident. You're just going to set it up the exact same way, and you just have slightly different values that you plug in. So you'd have negative 180,800 plus R T, ln of Q, but now your Q is going to look like that. Plus 26. Oh, gosh, almost identical in terms of the answer there. Also answer C. Uh, So now when titrating a strong monoprotic acid with KOH, so monoprotic means we have a single proton. So HCl, HF, or not HF, but HCl, HBr, HI, any of those examples, they're going to react with potassium hydroxide in a 1-to-1 ratio. Essentially, I've got a strong acid, strong base titration. So what will be true? The pH will be 7 at the equivalence point. And that'll be it. If the pKa for the acetic acid is 3.74, and we have a buffer of acetic acid and sodium acetate, and that buffer has a pH of 3.89, which of the following is true? Well, with the Henderson-Hasselbalch equation, I'm going to have 3.74 plus the log of the base over the acid. To get a positive value, the concentration of the base would have to be greater than the acid. Or in other words, I'm going to take 3.74 and add a positive 0.15 to it. But to do that, the concentration of the base has to be greater than the acid, which is right there, answer A. We'll get something greater than 1, and that log is going to be positive. If the concentration of the acid were greater, we'd get something less than 1. The log of that would be negative, and we'd have a pH below our pKa. What's the balance equation for the galvanic cell? All right, let's see. Okay, so we're given this. Our anode is nickel. Oops. And it looks like it's oxidizing to nickel 2 plus, and then we have our salt bridge, and then we have our cathodic side, and it looks like, oops, that's a gas. Our chlorine is reducing to chlorine minus. And since chlorine is a nonmetal and it's not conductive, our cathode is glassy carbon here. But that's just, there's the electrode that's not going to participate. So then the balanced equation is going to be, like I said, nickel is being oxidized. The nickel 2 plus, we would be losing 2 electrons. And then chlorine is being reduced. So each chlorine is going to go from 0 to -1. So gas, aqueous, that should look like that, which is right 0 to -1. Yep. NiCl B. No, B is balanced and everything else matches. Yep. So B. Standard EMF per cell using overall cell reaction below is 0.48. So what changes? Okay, so we're looking at E cell non-standard equals E cell standard minus 0.0592 V over N times the log of Q. Yep. So we're going from zinc to zinc 2 plus and nickel to nickel 2 plus. So our N is going to be 2. We're given our standard E cell as plus 0.48 volt. And then log of Q. Zinc 2 plus is our product. And nickel 2 plus is our reactant. So negative 0.0296 volts times negative 1.398. We're going to get 0.48 volts plus 0.04 volts, and then our answer should be 0.52 volts, which is right there, answer C. All right, nickel can be plated. How long would it take to plate? Okay, so we've got 29.6 grams of nickel 2 plus, and we are going to do 4.7 amps. So let's take our 29.6 grams of nickel and convert it into moles, dividing by the molar mass of nickel. 58.69 grams. Got about 0.5043 moles of nickel. Let's see, we want to end with time. So I think, okay, so we want to end with time in minutes. So we're going to go from minutes to seconds, to amps, which are 4.7 coulombs per second, to Faraday's constant, which is 96,485 coulombs, times, no, coulombs, kilomole have said then, 1 mole of nickel for every 2 moles of electrons. And we know that we started, did I go backwards? And we started with 0.504 moles of nickel. So if we take that, okay, so 0.504 moles of nickel times our 2 moles of electrons means we're going to have about a mole of electrons, which is going to give us 96,485 coulombs divided by 4.7 amps gives us 20,707 seconds, and then divide that by 60 to get minutes, should be 345 minutes, which is about 350 or okay, delta S for the following reaction. Delta S is on for each species, so basic again. Products 229.2, and technically there's just one of those, minus reactants. Here I'm going to have 1 times 200.9 plus 2 times 130.7. Oops, there we go. So gives us negative 233.1, which is answer E. What's the molar solubility of calcium hydroxide? Solid, it's going to go here, give us calcium 2 plus 2OH minus. So these are both aqueous, so I'm going to have S and 2S. And we have the case of KSP for calcium hydroxide and the page of constants. That's going to equal S times 2S squared, or 4S cubed. So take 4.68 times 10 to the negative 6 divided by 4, and then take the cube root of that. You should get 1.05 times 10 to the negative 2, or answer A. Let me make sure. Yep. Lastly, determine the equilibrium constant for the following ratio 298. So we're given our standard delta G. We're going to use this equation right here to solve for K. I'm going to have negative 34,500 joules equals negative 8.314 times 298 times the ln of K, which is what we're solving for. So I'm going to end up with negative 34,500 divided by negative 2,477.57, and that's going to equal the ln of K. So I've got 13.925 equals ln K. So then just take E of both sides, and I get 1.12 times 10 to the 1, 2, 3, 4, 5, 6. Yep, answer A. All right, so that should be everything there. Hopefully this was helpful. Similar-ish to the exam. That's the end of this.